You've all seen flashes of what our near future might look like. Jarvis, Vision, Ready Player One, and so much more. As our daily lives become increasingly intertwined with the internet, sparking innovation and enhanced human intelligence, so too will the machines we're surrounded by become intelligent. China's factory system, their jump from physical cash to facial recognition for consumption and purchases are daily processes that are the most advanced today. And all this boils down to neural networks. But what's this? Neural networks are defined as a series of algorithms that recognize underlying relationships in data by mimicking the human brain. In a real neuron, the dendrites receive electrical impulses from neighboring neurons and pass it on to the cell body. The all or none law tells us that the sum of the impulses received must be greater than a certain voltage threshold to be propagated down the axon to the axon terminal. If the sum is lower than the threshold, the impulse essentially dies in the cell body and does not get passed down. Basically, if the sum of the inputs x1, x2, all the way to xm exceeds the threshold within the neuron cell body, then a signal gets sent down the axon to output y1, y2, all the way to yn. A neural network is closely modeled after the same process. It also receives inputs x1, x2, all the way to xm. There's also the addition of weights, which are multiplied to the input received. The activation function determines the sum of the products of all the weights and inputs, and if the sum is greater than the threshold, the network is activated. Neural networks are organized in layers of nodes. While machine learning algorithms must consist of multiple layers, a neural network can function with just one. One type of artificial neuron is called a perceptron. They take several binary inputs x1, x2, and x3 and produce a single binary output 1. Along each path to the body of the perceptron are assigned values w1, w2, and w3, called weights. They're assigned values based on importance. As an example, suppose Coachella is coming to San Francisco. You want to have some fun, but there are 3 factors really affecting your decision. Will Blackpink be performing in 2021? Does your friend want to come with you? Is there going to be awesome food? Say you don't care as much whether or not your friend is coming with you or if there is good food. Blackpink is the driving factor behind your decision. Whereas factor number 2 and 3 are weighted at 2, you would probably assign a weight of 6 for factor number 1, signaling that you see it as most important. If the threshold value is 5, the combination of factor 2 and 3 being true will not make you attend Coachella. Only factor 1 being true will make you attend the festival. Everything can be summed up with this piecewise function, where the threshold is equal to negative b. So if our network outputs a binary digit 1, then the neuron fires. If the output is a 0, then nothing gets sent along the neuron. When we want to train a neural network to learn something, we adjust the weights with small changes to produce closer and closer outputs. By repeating this process, the network is learning. Up until now, we have been talking about a unit step threshold activation function, which a perceptron uses. The more commonly used function is the sigmoid activation function, which the sigmoid neuron uses. Instead of the output being 0 or 1, the output here is defined by, where sigma is the sigmoid function. Keep in mind that the x in the sigmoid function is equal to a weight times a binary input x1 plus the bias, which is the negative level of the threshold. So when x approaches negative infinity, sigma approaches 0, and when x approaches positive infinity, sigma approaches 1. At extremities, the sigmoid neuron acts like the perceptron. But now our question is, how large is the change in output compared to the change in input? We need the loss function. It measures how much precision we lose by looking at the output of our neural network compared with the actual output. So if our loss is huge, we did a bad job. But if our loss is approximately close to 0, our neural network was trained correctly. To find our loss function, we start with the definition of a derivative. Instead of delta x, we'll use epsilon for infinitesimally small changes in our input. By reordering the terms in our approximation of the derivative, we can find the change in the output in terms of changes in the input. Taking the expression we have just derived, we can relate it to our loss function. We will begin by using the partial derivative to denote that other variables within the function are kept constant. Looking at step 1, we have changed both weight 1 and weight 2 by an infinitesimally small amount epsilon. On the right-hand side, our function L no longer has epsilon 1 because we've rewritten our expression to equal what we derived previously. In step 2, We similarly rewrite function L with a change in weight too, so our expression now has two terms with partial derivatives of their respective weights. In step 3, we see that all terms with a partial derivative have now been summed up in a summation notation with all the weights in our function changed by an infinitesimally small amount epsilon. Looking at the right side of our equation, we can rewrite the summation using the dot product rule and rewrite all the partial derivatives for all the variables as the gradient, resulting in a loss function that looks like this. This tells us approximately how the function L on the left-hand side will change given any perturbation to the input. The L on the right-hand side is our loss. To minimize our loss, we need to find a direction V that decreases L as rapidly as possible. We'll call this our direction of steepest descent. We can rewrite our loss function from the previous slide as this, where an infinitesimally small change epsilon is now replaced by an infinitesimally small change in direction V. On the right-hand side, we'll see that once again, we've used a dot product rule where we assume direction V has a magnitude of 1 to make our computation simpler. If we want to find the direction that decreases L as fast as possible, we would have to make the expression as negative as possible by making cosine of theta equal to -1. And we'll see that the steepest descent points in the direction of. Our gradient descent algorithm seeks to change the weights so that the next iteration reduces our loss. So for our basic algorithm to train a neural network, we use the gradient to find the direction that decreases the loss as rapidly as possible, then update the parameters to take a step in that same direction. Of course, there's still more to building a functioning AI system or machine than just using neural networks. In the near future, AI will become more commonplace, replacing jobs but also enhancing our work. So what will our future look like? Will we be living symbiotically with AI systems and machines, or will their intelligence surpass that of mankind, bringing destruction to humanity?